Hello, I'm Professor Leslie Rusch from Université Laval in Quebec City, Canada, and I'm here today to talk to you about silicon photonics enabling 5G optical networks over a passive optical network infrastructure. I'd like to take this opportunity to thank the organizers of this conference for allowing me to speak to you today. It's just a shame we couldn't all be together in Gothenburg, such a beautiful city. I'd also like to acknowledge my co-authors, so Senior Researcher Sun Guan and Professor Wei Shi. So here we have the diagram of a 5G network. We have on the left all of the users, the things that we connect to, either people or machines. We have on the far right a distant cloud where computational resources are available to improve the services. And in between, of course, we're talking about wireless 5G. We have a system of antennas that gathers this information and has a connection to the cloud. What we define as the edge of the network is this proximity between the users and the antennas. And of course, the cloud is much distant. So we're going to be talking today about smart edge computing, where we locate some of the computing resources. Instead of leaving them out in a distant cloud, we bring them to a smarter edge. And in particular, what are the requirements for 5G and for the optical transport in such a situation? So here's an outline of what I'll be talking to you about today. I tried to organize it around a series of questions. So the first question we're going to answer is, how do we evolve to a radio access network with a smart edge? So I'll talk in general about radio access networks and get us to the smart edge. Then I'll take some time and tell you why the smart edge is so important. What is it that we gain when we add a smart edge to a radio access network? Next, we'll confront the question of how can we exploit a PON infrastructure for RAN. So there already exists a lot of deployed fiber, and can we support a RAN, can we support a smart edge using this infrastructure? The next big question is, how can silicon photonics enable this radio access network smart edge? Because of the advantages of integrated devices that can keep costs down. This is an important aspect of why Cloud RAN is now a very interesting solution. So then I'll talk to you a little bit about some research we've done recently. Where do we stand now? And the last question, is it really that simple? What's left to do? I'd also like to mention that we have a new communications magazine article coming out next month. Well, this month, but it's a bit delayed, so the June issue. And everything I'm talking about today is covered in this article as well as in the proceedings of the conference. They're kind of complementary. So, first question, how do we evolve to a RAN smart edge? So the idea is that we take edge computing. Why do we put the computing power at the edge? It's because of the tight latency requirements for certain applications, and in particular for 5G applications, and also the requirement for high computing power in order to enable new services, new capabilities. So the cloud is basically too far to respect these tight latency requirements, and the mobiles themselves, they're too limited to be able to do all the computing that's needed. So we're looking for like a Goldilocks solution, something which is got some computing power, maybe not as much as in the distant cloud, but still more than a mobile, and close enough so that these latency requirements can be respected. So we're looking at the configuration of a radio access network. So it's going to have similar attributes to what we think of with cloud processing at a distance, but now we're going to use this edge computing in particular for the radio signals. So the new problem that we have to solve with this smart edge is how to optimize the 5G remote antenna sites. So let's start going through how do I use the cloud, how do I use wireless services. And the first one I'm going to do is really when there's no radio access network. What we've got here is an antenna site, an antenna tower, and we're going to call the remote unit to be the processing that's done at the antenna site. And in the when there's no radio access network, that means that there's an optical fiber that goes from this site, and it's basically doing what we call backhaul. So all the processing has been done at the remote unit, and we have digital backhaul to the core network where we'll access information in the cloud. Now, when we start to evolve to the RAN, we're going to look at some of the processing that has to go on at this antenna site. So RU, remote unit, really is the minimum. That's like the antenna. But in addition to that, of course, we have to have the central unit and distributed unit, which handles, the distributed unit would handle a lot of the physical layer processing. The central unit would handle a lot of the network layer processing. But basically, all the baseband processing is local here. It's all being done at the antenna site, and the backhaul is strictly digital. So all the compute power must be located then in this scenario at the antenna site. So if I have applications running that have tight latency requirements, and I cannot get the computing power in the core network to help me there, I can install what's called a MEC unit, which is computing power, which I can locate at the antenna site. So when I have this, no radio access networks, there's no latency issues because I put everything right next to the antenna. So of course there's no latency, and there's no bandwidth because I don't have to transport anything. All of the processing is being done right at the antenna site. Now, the problem is that this requires very complex hardware at the antenna site, and there's no RF coordination among multiple antenna sites. So of course these antenna sites can be quite remote, can be difficult to access. Maybe they don't have air conditioning. It may be the MEC processor may be very difficult to service in these locations. So it's not the most ideal scenario for putting in this distributed computational power. So now we start coming to the reasons for using a radio access network. So here's the first idea of radio access network, and we are introducing what we call the Smart Edge, which is somewhere between the antennas and the users and the distant core network. So we're going to call something, this mid-haul is the optical fiber, which will be carrying information from the antennas into this Smart Edge. And once again, we can see this division of different functions in the processing of the wireless signals. But now instead of them all being located at the antenna tower site, we're actually splitting some between the antenna site and the Smart Edge. So for instance, there is this distributed unit. Remember I said the distributed unit is mostly physical layer. And then the central unit we push back to the Smart Edge so that some coordination can go on at the network layer here. And of course, in this scenario, all baseband processing is still very local. Now, this distance is chosen to be short enough that the latency requirements are met, but the computing power can now be located at a convenient location. So if the antenna tower is remote, difficult to reach, this could be in a cabinet, in a building, where it's easy to update your hardware, your commodity computer processing hardware as it becomes higher performance, lower cost, lower power. All of these things can be easily adjusted. So again, proximity is giving us latency requirement, and there's no bandwidth issues on this fiber because it's carrying basically digital data. There are no radio frequencies which are being carried on this mid-haul. But because I'm not carrying radio signals, that means there's no RF coordination. Even though I have a Smart Edge which has a connection to multiple antenna sites, I'm not able to coordinate at the RF level. Of course, with the central unit, I'm able to coordinate at the network layer, but not at the physical layer. So that brings us to radio access networks with Fronthaul. And this is the model that we moved for as being the highest performance and able to really achieve the goals of 5G for increasing capacity. So in this vision, we've moved the distributed unit into the Smart Edge now. Now we have, again, the same fibers are interconnecting, but now the data that's being carried on these fibers is the native radio frequency signals which are captured by each one of these antennas. That means that when I go to the Smart Edge now, instead of having a DU which does baseband processing just for one antenna, we can now do baseband processing which is optimized across all the antennas in the system or that are connected to this Smart Edge. All the antennas vision of the radio signals over a much larger geographic area. And this box here called COMP, I'm going to be talking about more. This is how we can take that data that is being delivered, the radio frequency data, and be able to achieve so much more. So the nice part of this RAN is that we have extremely simple hardware at the antenna site. We basically just have something that will convert from an RF signal into an optical signal. And then all the intelligence is now centered at the Smart Edge. And not only can we do network layer coordination, we can also do RF coordination, as I mentioned. Of course, this RF coordination has some very tight latency requirements, but because we're at the edge of the network, these distances for the fronthaul are not too long, and this is a very good solution. So that's how we evolved into a radio access network, why we did it, and what it looks like. Let's go on to the next question, which is what can we gain when we use this Smart Edge? So, of course, we have edge computing. We have this compute power. And so this multi-access edge computing, this MEC unit, is using that compute power for applications. But now we can also use that compute power to do the digital signal processing, the baseband processing for the 5G physical layer signals. I'll be talking a little later about how we can actually use this approach to densify the network. In other words, to be able to handle many more antenna sites, to create ultra-dense picocells, because that's another way that we can increase the capacity of a 5G network. And in order to be able to densify, we have to keep the units, the remote units at the antenna sites, as simple as possible so that we can populate more and more antenna sites. Now, remember that box I said was called cooperative multipoint, and that's a lot about what we gain at the Smart Edge as far as what 5G signal manipulation is all about. So by doing digital signal processing at the Smart Edge, we can coordinate, as I mentioned, on the RF level. This will reduce the intercell and intracell interference and enhance signal quality, which will let us get to faster transmissions and more dense transmissions. So I call this COMP, and I'm going to, since this is a tutorial, I'm going to take a little bit of time to explain to you what is being done with that coordination and why it's so important to keep the latency very low for these applications. So coordinated multipoint coordinates transmissions at the RF level, and there's many ways to do this. Let's take this one simple way is beamforming with multiple antennas. We can think of sectorized antennas which only look in a certain direction, but beamforming is a more powerful solution, and it's like a programmable way to do sectoring. So let's see what that means. Suppose I have just two antennas at my cell site, and I have a mobile unit, which is my target, another antenna, and I want to enhance my communications with that target antenna. Well, what I can do is I can send the same data to both of these antennas, which are pointing towards my target. Now, in each of these antenna chains, I'm going to manipulate the same data in a different way for one antenna versus the other antenna. And the way that I manipulate it is determined by the actual channels. And of course, two antennas will see two different channels as it communicates to the target. So depending on what that channel looks like, I adjust the phase and the gain of my signal to really enhance the signal which is going to the target. So the gain, the antenna gain to that target is much enhanced. So instead of being one physical antenna, I have two antennas, but they're working together, so they're like a virtual antenna. And here I've shown you the illustration with just two antennas, but of course we can expand this to multiple antennas. And the more antennas I have, the more directional a beam I can create, and the greater the gain is in the direction of this beam-formed signal. So that's one way of looking at it, but I don't just shape it to one target. I can shape it to each one of the targets. So I have a large array of antennas, and the signal that I send, instead of sending, you know, a omnidirectional signal to cover all of my different mobiles, I actually shape it so that most of the power is going in the direction of the mobile. And what's really great about that is that the signal I'm sending here to mobile A is going to have much less interference given to mobile B because of the shaping of the directionality. So this coordination at the RF level I can only achieve by having good coordination. Of course, if I had it at one antenna site, I could do this, but I want to do even more. I want to take advantage of multiple antenna sites. For instance, I could have multiple antennas, each one shaping it towards a given mobile to enhance the performance. And so the coordination and of course more digital signal processing, all of this processing uses more compute power, which now is available to me in a very efficient, low-cost smart edge. So in order to do all of this nice DSP, I need to have what they call a channel state information. And this is the kind of information that can be shared across different radio heads, so that we're taking it as much advantage. Each radio has a vision into the each one of the mobiles that is in a joint coverage area, and the central processing can really take out the most possible from this scenario. So of course that's just beamforming I've been talking about, and there's much more that we could do than even just beamforming. We can use pre-coding as well. So when I said beamforming, I said we were sending the same data to each one of the antenna. However, we could do something called multi-stream so that it's not at the same time necessarily. There could be different delays, and that I could play on the delays in order to increase performance. And in fact, when I do this, it works even when there's no line of sight. Remember when I was steering this antenna, of course I had to be able to see the mobile in order to really point at it. But when I introduce pre-coding, this allows me to deal with a multipath channel where things might be blocked, but I can get around it by reflections. So that's one way, but another way is to do what's called spatial multiplexing. And I don't have time to go into all of that today, but spatial multiplexing is a way to take advantage of multiple antennas at the receiver and at the transmitter, and to use multi-input, multi-output digital signal processing in order to, again, enhance the performance of each one. It's almost like creating a different channel for each one of those antennas. So you can see that antennas are the key to really pushing the performance of the wireless system, no surprise there. And one of the ways that we can do the most of it is by applying a great deal of signal processing. But all this signal processing really needs channel state information, and the more that we can share across antenna sites, the better performance we'll see. So just to go back, make sure we're all playing at the same field here. We have a distant internet, we have some central office, and a remote node, which is connected to the antenna sites. We're talking about separating the remote unit, which would remain only at the antenna site, and trying to find a good home for the distributed unit and the central unit. So where could we put that home? Well, if we put it at the distant internet, it's too far away. Latency is way too high. That radio signal, cars zooming by, people walking around, it will be completely changed by the time I'm trying to do any sort of shaping. I can try and do it at the central office, but again, the latency is just too high for me to really be able to do baseband processing something like 80 kilometers distance. So that's why we're looking here at the remote node. And at the remote node, if we turn that into a smart edge and we put our baseband units there, our DU and our CU at the smart edge, now we're looking at distances, under 20 kilometers, and the latency is low enough that we can support certainly applications, but also this kind of RF coordination we need for 5G to really push the boundaries of its communications capabilities. So that brought us to this Fronthaul vision of the radio access network. So, next question. How can we exploit a deployed PON for a radio access network? So, Again, remote unit, that's the equipment that's high in the antenna tower. The distribution unit, that's the baseband signal processing that we're proposing to do at the Smart Edge. So the fronthaul, which carries the data from the remote unit to the distribution unit, that fronthaul must carry radio signals over the fiber. And do we do this in digital form or do we do this in the native analog form? That's one of our questions. And if we look at the digital form, this has been the way that radio access networks were first conceived, and to use something called the Common Radio Interface, CPRI. And if we look at the remote unit, what is involved when we use the CPRI protocol? Well, it has certainly the RF chain, so I take my RF signal, then I do an analog to digital conversion. Now I've got digital data, and I just use my electric to optical conversion like I would on any kind of digital data. When I get to the distribution unit at the Smart Edge, I convert that optical signal into electrical, I go from digital to analog, and now I do my baseband processing. The problem with this is that the standard was written in a way that is really bandwidth inefficient. Unfortunately, if we look like something for a 10 megahertz signal in the RF domain, by the time it gets put onto the fiber, we're looking at something like 1.2 gig if I'm looking at a 2x2 MIMO situation. So, big expansion, and if, as I add radio units, I'm getting more sophisticated radio units with more antennas in an array that I'm trying to exploit, of course, every 10 megahertz channel ends up requiring a different signal for each one of the antennas. And so this bandwidth expansion becomes really critical. And this is what's getting in the way of really exploiting radio access networks which involve fronthaul. So there is what we call the enhanced CPRI. And the enhanced CPRI reduces this overhead, the spectral efficiency, and it does that by putting some baseband processing at the remote unit. So I put sort of a lowercase bb, so a little bit of baseband processing. There's still a lot of baseband processing which is going to be done in the Smart Edge, and certainly all the coordination is going to be being done at the Smart Edge. But other than that, the rest of the elements stay the same in the enhanced CPRI. So I'd like to propose another approach, which is to use the analog radio over fiber approach. And the advantage of this is it can be much more bandwidth efficient, that we don't have this overhead of trying to convert into a standard digital format. So it certainly is better than CPRI, probably a little bit better than enhanced CPRI, maybe the same, I'm not sure. But we can see an advantage in the complexity of the remote unit. So one of our goals is to increase densification, to have a lot more antennas. And to have a lot more antennas, I have to have each one of the antennas as simple, low cost as possible so they're easily deployed. So this approach with the analog, of course, eliminates the A to D at the remote unit. And from a power consumption point of view, of course, clouds are very power consuming, and of course I wouldn't have to have the digital to analog conversion. So I'm saving both power and cost by going to an analog radio over fiber solution. So our proposed solution is use analog, don't use the digital CPRI, and this will keep remote units simple. But now I'd like to talk to you about another level of complexity, if you will, and that is to exploit the passive optical network infrastructure of deployed fiber, which is available and has unused capacity. And we're going to talk about overlaying analog radio over fiber signals in this spectra that's available in the passive optical network. So consider a future WDM PON once we've tried to increase the capacity of the PON by using multiple wavelengths. So we have, of course, our core network, go to the central office, and at the central office we will have multiple wavelengths. They'll be combined in an array waveguide grading, sent over a feeder fiber to the remote node. At the remote node I have another AWG which now separates each one of the wavelengths and sends it on a drop fiber to each of the ONUs, optical network units, which receive this signal. So if I take this vision of the future, more wavelengths, more capacity, so maybe we would be able to accommodate more than just the digital services. So first of all, for sure, I could make one of these antennas my client. So they could be a client on the PON, in which case, this is back to not a radio access network per se. I've just got, a backhaul here, but the backhaul goes to this remote node, and I can take advantage of this existence of a cabinet or a room or available in a building to upgrade this remote node and to turn it into a smart edge. And how do I do that? Well, I just put some compute power in this location. And so then my clients who are radio towers can use this as mid-haul and create some good advantages to using the passive optical network infrastructure. But that's not really what I want to talk about today. What I want to talk about is densification. And densification means adding a whole bunch more of small antennas. Now imagine that I have a client, and outside of that client for digital data, I put in an antenna or multiple antennas, and that these antennas are going to intercept the radio signals which are coming from this smart edge and are going to use them as 5G. And then the client, of course, is going to continue to have the typical internet service which is provided over the passive optical network. So this overlay, what is the idea of an overlay? Well, I have, tunnels that are on each wavelength that goes from the central office down to each one of my ONUs. And what I propose to do is to take that smart edge and add a little analog radio over frequency from this smart edge. So to create locally what the radio signal should be and just send the radio signal right to the antenna. So this is a more challenging situation than just having a client on mid-haul. So now this is really front-haul, and on the front-haul I'm putting this analog radio over fiber. So now we have our next question. Can silicon photonics enable a RAN smart edge? And it will come as no surprise to you that the answer to that question is yes. Yes, indeed, it can. So what are the challenges in dealing with passive optical networks? Well, passive optical networks are typically single feeder networks. That means we have one fiber for both the uplink and the downlink. We'd like to keep the cost of the passive optical network low, and in particular we're examining solutions which are extremely low complexity at the ONU by using colorless operation in the case of a distributed carrier. So there's absolutely no source at the ONU. Instead, the laser source is sent from the central unit. It's used to facilitate direct detection with beating against this carrier that's coming on the downlink, and then to use remodulation of that same carrier for the uplink. Now, what we're looking at, of course, is the very challenging overlay system where we have to coexist with the existing paying customers which are getting digital transmissions, and we want to piggyback onto that without disturbing that customer base to add this analog radio over fiber signals. So here's this tree architecture diagram that we've shown already for a passive optical network. We have the central office, and I'm going to put that over here on the left. Then we have the smart edge. I'm going to put that in the middle. And the ONU, the customer premises device, I'm going to put here on the right. So I'm going to show you the architectures we're proposing for the silicon photonics to enable this overlay services, heterogeneous services on the same passive optical network. And for that, my proposal is going to be centered on the use of microring modulators. Now, the reason for this focus on microring modulators, microring resonators, is due to the particular application of passive optical networks where cost is a big driver. And size also, if we're going to WDM and we want to scale up, it's important to keep size small, and power also, to try and keep power consumption as low as possible at these, in these units. So here are the three different subsystems that we're proposing in silicon photonics, and I'm going to take them one at a time and step you through how microring resonators, microring modulators can be used in this context. So let's start first with the central office. And in the central office here, you can see we have a cascade of microring resonators, and in this case in a Mach-Zehnder MZI architecture, and that's because we're going to be doing complex modulation I and Q. So first of all, I'm going to discuss why microring modulators. We also have the option in silicon photonics to look at Mach-Zehnder modulators. So here would be the Mach-Zehnder solution, and up here is, of course, the proposed one in microring modulators. So if I used a comb source in the case of a Mach-Zehnder modulator, I would need to add an array waveguide grating, an AWG, in order to take these combs and separate each one of the comb lines so they could each one be modulated by a different Mach-Zehnder. And then when that was all done, being modulated, I'd of course have to combine them again with another AWG so that they could go down the feeder fiber. Now let's look at the proposed architecture. In this case, we take that laser comb source and we do not have to demultiplex the wavelengths. Instead, we exploit the wavelength selective feature of the microring modulator in order to tune each one of the modulators to one of those comb lines. And so the modulator will act only on one comb line and leave the other ones untouched. And in that way, we can easily scale by just adding microring modulators. So I mentioned that we chose this IQ structure, and the reason that we are interested in the IQ structure is due to the chromatic dispersion induced fading in short distance PON feeder networks. And in this case, the IQ, this fading can be bypassed by using single sideband modulation. It's the double sideband modulation that gets you in trouble. So if I use single sideband modulation, I won't run into this fading, and I can still have a very cost-effective solution using direct detection. So the IQ is not made to do phase modulation, but instead it's to do sideband suppression. So we see here a little cartoon, which is the frequency spectrum as we send our comb line through this cascaded bus of cascaded microring modulators. So after the first pair, IQ pair of the microring modulators, we have a nice single sideband due to the modulation that the combination of the two modulators. Any one modulator will give you double sideband, but the way we combine them allows us to eliminate one sideband. And as the comb laser source is going through this chain, each one of the modulators can add its own digital services in the form of a single sideband modulation. So now let's move to the Smart Edge. And in the Smart Edge, we've got, again, a bank of different cascaded modulators and certain modulators for each one of the WDM channels that we're going to be supporting. But in each channel, we actually have multiple microring modulators. And let me explain how this works. So we can see coming in here into the Smart Edge, we have these single sideband modulations on various wavelengths. And we go through our first microring modulator, and the goal of that first modulator is simply to create subcarriers that are going to be used in the same WDM slot in order to modulate the radio over fiber signals. So here are two subcarriers that have been generated. And again, the important feature as we go on, as we go through these microring modulators, is that the original services not be disturbed. So we want to have these broadband signals, this broadband signal we see here, untouched by all of these other manipulations that we're doing. So certainly we can see here that even after the subcarrier generation, this downlink is unperturbed. Now each one of these modulators in turn can add a radio frequency signal. So here we have one in baseband for illustration. Here there's one on the RF carrier as well. And this that we're seeing now is how we're adding what I called this little overlay in the WDM slot. And of course the adjacent channels are all untouched because I have only tuned this one to one of the comb lines. And if I want to go on and provide each of our clients with a different radio over fiber service available, then I would just add these different channels for each one of the WDM, the wavelengths that we're interested in. So finally, let's look at the ONU. What's the architecture that we're proposing to use in each one of these dropped fibers? So we have again a cascade of microring resonators and microring modulators. The microring resonators are used as filters in order to drop the signals. We have multiple signals, we have to separate them and drop them independently. So the first microring resonator, for instance, could drop the digital services for the existing clients. The next microring resonator could drop one of the RF. The next one could be tuned to filter out and drop another ROF frequency. And after all of these signals have been dropped, what's left is the carrier. And the carrier then goes into a microring modulator, which does the uplink. And again, we're going to use IQ so that we can use single sideband modulation for the uplink. So this is a fully integrated silicon photonics solution, and because we're using this distributed carrier, there's no problem with not having a laser source available in the silicon. So now I've shown you the solution, what the architecture looks like, and the next question is, well, where do we stand now? How do we, have we demonstrated that this is possible, and where does the technology stand today? So again, I'll take you through each one of our subsystems. Let's start with the central office. So there's been a lot of activity that has looked at how do you take a comb source and modulate them with microring modulators. And Dong in 2016 was looking at discrete multitone, and he looked at something high bit rate signals. And in that case, I think he used one laser and tuned it each differently, but the concept was certainly there. And Chen, around the same time, was looking at on-off keying for the same idea. With MRMs, in this case spaced very at 240 gigahertz, and he did a 2-channel demonstration. More recently, there has been work by Kong looking at a comb laser generated by phase modulation, and in this case there was 4-channel demonstration, and again very high bit rate. We have been looking in particular at single sideband modulation, so we took our IQ formulation, Mach center interferometer form for the 2 microring modulators, and demonstrated that we could get very good sideband suppression over 18 dB when using them to avoid chromatic dispersion induced fading. Let's move now to the Smart Edge, and at the Smart Edge we have done some experimental demonstrations to show this concept of overlaying analog radio over fiber signals. So I refer you to our publication in order to get details about the microring modulators that we designed, we had fabricated, we put them into a system in the lab, and this is what our experiment looked like. We used a digital to analog converter in order to generate our broadband digital signal, and we used another channel for that DAC in order to create the radio over fiber signals. And those radio over fiber signals we put through our chip with multiple microring modulators in a bus configuration. For the ONU, we used a programmable wave shaper, which allowed us to pick off each one of the signal types, radio over fiber or digital broadband, in order to do detection and validate the good performance. So, once again, the first modulator's role is to generate subcarriers. And we studied how to operate the microwave modulator in order to keep the parasitic harmonics as low as possible and to keep them from interfering in the operation that we've proposed. We also looked at the kind of distances between the subcarriers. Of course, that's easily controlled by the clock frequency going into the microwave modulator. So here we're going to step you through what's happening with the whole cascade of microwave modulators. So here we have a cartoon of what's going on, and then of course our measurements are here up at the side. So in the cartoon we can see that coming from the central office we have two carriers, and each one of these carriers has a single sideband modulation on it. And if I go through the, so what's coming from the central office are these two broadband signals and the carrier. So we see the carrier here, and then here is the broadband signal. And we also have the next modulator that goes through, and after the carrier has been created, it modulates, in this case, a baseband 5G signal onto one of the subcarriers. And the next microwave modulator, in this case, puts on a 5G signal, not in baseband, but on an RF carrier. So we could do this, of course, by tuning them. We could put this on one of the wavelengths in the comb, or we could put it on another wavelength in the comb. So we can do this simply by tuning the microwave modulators. We did a second demonstration where we had another chip we designed, this time with a monitoring photodiode on the chip. So in this case, we were able to look at the thermal stability of a microring modulator. Of course, this is one of the big challenges in working with microring resonators. Is the good part is the wavelength selectivity, but the bad part is that you have to keep it stable to stay on that wavelength. So with the monitoring photodiode, we were able to get a signal out of the chip that we put through an algorithm to generate a control signal that kept us locked onto the subcarrier for the modulation. So in this case, for instance, we had gotten our reception of the radio signal at some nominal level. We introduced a step change in the thermal environment of the chip, and because of that, if we had no stabilization, we saw that our bit error rate, we turned off our stabilization, that the bit error rate deteriorated and never came back. But when we turned on our feedback circuit, in that case, of course, we lost it momentarily and then very quickly returned to good bit error rate performance. So finally, let me turn towards the customer preferences, the ONU, and look at what silicon can do in this place, in this role, for the overlay system that I described. So there's been other activity looking at silicon photonics for ONUs. Of course, this was not for radio over fiber overlay, but it was still a great project to look at how we could do reception of broadband signals using silicon photonics. So this was the fabulous project run by Roberto Guandino at Politecnico di Milano, and of course several other co-PIs. So in their demonstration, in their project, they looked at a microring resonator filter, and they used this to drop one of the WDM signals, and then they had a Mach-Zehnder modulator which would modulate for the uplink, and they also had some monitor photodiodes on chip to help with these filtering functions. They had very nice polarization insensitive design, and they did use on-chip amplification for their demonstration. So we're looking at the application of overlay in particular, so that at our ONU, not only do we have to drop one particular frequency, but we're also looking at dropping different kinds of services, heterogeneous services, broadband as well as narrowband radio over fiber. So because we have these two different functions we have to perform, we used a tunable version of the microring resonator. Not only could we tune the central frequency by thermal properties, but we could also adjust the bandwidth by the relative centering frequencies of these different elements in the microring resonating filter. We also designed a microring modulator for the uplink, and again I refer you to our publication for more details about the design. But it was fabricated and tested in our laboratory. So let me start by showing you our experimental results. Let's focus on this tunability of our microring modulators. Microring resonators. So here I show the first one in the line being that which does filtering of the radio over fiber signal, which is much more narrow band. So you can see it has been tuned to have a narrow band response and of course to be centered on the subcarrier generated at the Smart Edge. And this second set of microring resonators has been tuned to have a very broadband response for the broadband signal. So next, let's look at how our signals were sent through this chip. And this is the signal that comes from the Smart Edge. So there are three components to it. First, we have the very broadband standard passive optical network digital signal. In this case, single sideband, and I think it's OFDM signal. And we also have here 5 radio over fiber signals, which were added to a subcarrier in that WDM slot. And of course, we can see a very strong carrier, the distributed carrier coming from the central office. So we take this signal coming from the Smart Edge, and we put it through the first set of microring resonators, and the goal now is to get this filtering that we see in orange. So we filter off and drop the 5 radio over fiber signals, and of course a bit of the carrier power as well in order to do direct detection of these ROF signals. So this is what the signal looks like as it exits that first microring resonator set. And you can see here that the radio over fiber signal is greatly suppressed. It's been dropped. We've had some loss of power in the broadband signal as well from the roll-off of that filter that dropped the radio over fiber, but still strong enough for good detection. What's also interesting is that when we were doing the detection of the radio over fiber, of course we needed some of the carrier to do the direct detection, and we were able to peel off, just reduce the carrier by 4 dB, and that was sufficient to get very good reception for our ROF signal. Now we go into the second set of microring resonators, and now we have dropped our broadband signal. And when we drop the broadband signal, you can see now it's no longer present on the bus. And in doing this, we only needed to reduce the carrier by 2 dB, which means that as we go into remodulation, we still have a very strong residual carrier for the uplink. So next we demonstrated the uplink using this microring modulator. And you see here again a little bit of the residual OFDM signal. There's some of the residual radio over fiber signal, but you can see that we have a good 13 dB of suppression even on the previous radio over fiber. And here what we're looking at is the remodulated uplink radio over fiber signal. We've not been able to do one experiment where we take our chip for the Smart Edge, send it through some fiber, and then use our chip for the ONU. It's because our chips are not packaged and they're very lossy, and because of this there's just too much loss to do that kind of demonstration. So what we did instead is we went back to this idea about how can we examine very power efficient, not using much of the carrier so that we don't require amplification necessarily for the uplink. So we did this demonstration, and here we had radio over fiber signals, wideband signals on 2 wavelengths, so 2 fully occupied WDM slots. And we used at the ONU, now we used a programmable wave shaper. We programmed it much the same way as we would have tuned the microring resonator design. And once again, we played a similar game of trying to figure out how to take off just enough carrier to not deteriorate the remaining signal, etc. So here is the experimental spectrum of what we generated, and here's our examination of the how much we drop, what the performance impact is, etc. So it's taken me almost to the end. I'll say just a few words about, is it really that simple? And of course there are some aspects of this work which I have brushed aside, which are still challenging, which remains, but that just means that there's more work for all of us in this area. So very quickly, what's important is the stability issue for microring resonators and microring modulators. So certainly we have used on-chip monitoring diodes, photodiodes, in order to create a feedback signal. But as we scale to more and more channels, and we have more and more resonators, well, we want to keep the footprint small so they're packed kind of closely, and there's a lot of thermal crosstalk, and so we need some more demonstrations that show that this is as scalable as we believe it is. Certainly more control will add to complexity, but as this is a completely integrated on silicon, it could have the feedback control signals in CMOS. They're very slow, so they should not add to the cost significantly or the consumption overly. Another challenging aspect in working with silicon photonics is the polarization sensitivity of silicon. It only supports one polarization. So we need polarization diverse designs. There are several that have been demonstrated. I mentioned the one from Fabulous earlier. But of course, it's easy to do some designs which are just to multiply the number of components. But we'd like to do something a little more clever that keeps it very efficient, keeps the footprint small. Of course, the footprint's small, the power consumption is low also. Very, very important. So let me just conclude by reminding you that what we saw was an architecture that lets us merge a smart edge and radio access network concepts with an existing PON infrastructure. So we know that this is important because it would allow us to have dense cells, because it would allow us to have very, very simple radio units, which could be deployed at very low cost and could be deployed to sites on the existing infrastructure. So really interesting way to densify the network without adding too much to the cost. In order to use this idea of a smart edge and a radio access network, of course, we have to deal with Fronthaul. And in Fronthaul, we have to be spectrally efficient if we're going to coexist, if this infrastructure exists, but it's occupied by digital subscribers. And we want to have an efficient Fronthaul so that we could not take up too much spectrum as we add these radio over fiber signals, which is why we proposed the analog radio over fiber. We saw that this idea of a smart edge is really critical for 5G because it allows for coordination. Coordination that only happens when you have a front-haul link. Mid-haul link won't give you that added performance. And again, we demonstrated experimentally that it is possible to overlay on an existing PON to leave the digital subscriber unmolested while we add the analog radio over fiber signal. So silicon, we showed, is able to do this, and it's a great enabler because it can keep costs low. We looked at micro-ring resonator structures because these devices are small footprint, they have low power consumption, which means that the OpEx will be low, the operating expenses will be low, but because they're also very small, that means that the cost of the devices will be low. So the CapEx stays low. And of course, when I did all of this proposal for an architecture, it was always an architecture which is compatible with WDM. Of course, we can do this with one wavelength, but what we wanted to have is a solution that was scalable to future networks, which is compatible with multiple wavelengths. And of course, the spectral efficiency was very important to have efficient Fronthaul so that we could be able to support many antennas, to be spectrally efficient, to be able to put them and support many signals. So finally, thank you to the audience today, and thank you to my sponsors, to the Canada NSERC for funding, and to the Quebec Prompt program, and of course our industrial sponsors, TELUS, an internet service provider in Canada, and a startup, Optical, working in the PON sector. And finally, I'd also like to mention that if you'd like to see this presentation, it's also available on my YouTube channel. You can share it with your friends or look at it again. So thank you again for your attention, and I'd be happy to answer some questions now.